Okay, welcome to today's webinar. So let's start. As usual, there's a live chat together with this webinar. Let me just start the screen sharing so that you can see what I write here. So there's a live chat on chat.tum.de. Please find the channel MA9714-CE for the central exercise session. You're welcome to ask your questions there, and I'll take the questions from there. The chat will be moderated as usual, and this time Fabian Scheib is going to be our moderator, so he'll forward the questions to me and he'll hopefully answer other questions that you might have. Fabian, would you introduce yourself, please?
Yes. Can you see me?
I can see you.
Perfect. Then, yeah, I think some of you already may know me from the tutorial sessions the last 2 weeks. So I'm a PhD student at the math faculty, and yeah, I will moderate the chat on Rocket Chat today.
Okay, thank you very much. One more thing I'd like to mention before we continue with today's sheet is there are e-tests available on the Moodle page now. So whenever you feel you're ready, you have understood the topics discussed in the first week, in the second week, and so on, there is a test available, a brief quiz on Moodle, where you can test whether you really understood everything with a few small examples. So I'd like to encourage you to complete these tests to see where you're standing. And as always, if you have any questions on these, then you're welcome to drop by at the tutorial sessions on Thursday. So let's start with today's exercise sheet. Sorry. Just scroll past this one. So the first problem on the sheet is C36. That's a problem on matching graphs, level sets, and functions. And before we start with that, I'd actually like to invite you to give a little feedback. Let's see where that is. So I've prepared a poll to ask for the main difficulties on this sheet. I'll just start that one. So the question is, what type of problems did you have the most challenges with, the most difficulties with? It may be matching functions, graphs, and level sets, like the one problem that we are going to discuss next, or the notion of open sets, closed sets, bounded sets, and so on, or the computation of accumulation points of a sequence. So let's see. Okay, I'll give you 10 more seconds to cast your vote if you haven't done so yet. Good, so let's close the poll now. And let me see if I can give you the results. Yeah, you should see the results now. So open, closed, bounded, and compact sets were the most difficult thing for you. That's going to be discussed in the next exercise, 3.7. So whatever questions you have, I'll be happy to answer those, hopefully, when we do this question. And then also accumulation points of a sequence. I have not prepared a central exercise question for that. Maybe I should prepare something for next time then. Okay, I'll make a note of that. We'll see if we have time for that. Okay, so let's start with 3.6. So I can keep this relatively short, if you're all familiar with that. So let's do this all together. Basically, we have 3 different functions. F1 of x1, x2 is defined as x1 plus 1 squared minus x2 minus 2 squared. Then F2 is defined as minus x1 plus x2. and F3 is defined as x1 plus 2 squared minus 2x2. And the task here is to match the surface plots that you can see on the sheet and the level sets that you can see on the sheet to these three functions. If you can't see that on the sheet, I have those plots here. So that's one of the level sets, one of the surface plots. That is one, and that's the third one. And here's the corresponding level sets. And let's see what functions could fit to those. If we look at the functions here, what we can see is the first function has two quadratic terms, basically. There's this term here, the x1 plus 1 squared term. So x1 enters in quadratic form. And here's the x2 term. Also, x2 enters in quadratic form. So going along the x1 axis or going along the x2 axis, one would expect the function to behave like a normal one-dimensional quadratic function, basically. So it should have a parabola shape along these axes. For f2, in contrast to that, both of these variables enter just linearly. Yeah, so there's minus x1 plus x2. So again, for both axes, one would expect the function to behave linearly. And then f3 is basically a mix of those two extremes. So here we have x1 entering with a square. That's the quadratic part of the function. So if we walk in along the x1 axis or parallel to the x1 axis, then you would expect the function to behave like a one-dimensional parabola. And walking along the x2 axis, this is just a linear term. So the function should be linear in x2 direction. So let's have a look at the graphs and see what graphs fit which description. So this one first here. Obviously, if we walk along x1 axis, we're basically walking along the lines of this grid that you can see here. And as you can see, that's just a straight line. So this represents a linear function along the x1 axis. Let's see if I can mark this a little. So here are the x1 parallels. And the same is true for the x2 parallels. This is an x2 parallel here. And you can also see this is just a straight line. So the function, this function here behaves linearly in both directions. Okay, so that should be f2. Let's look at this surface plot here next. If we again restrict this to looking at the plot in x1 direction, that means we're walking along one of these lines here, like this one. No. Like this line here, for example, or this line here. So those are the x1 parallels. Oops. Slipped a little. Okay, and as you can see, these lines basically are formed like a parabola. Yeah, so coming from the left, and there's the apex, and then they're starting to rise again on the right-hand side. Okay. In contrast to that, walking in x2 direction over this surface. So following one of these lines here, like this one or that one here, you also get a parabola, but it's turned upside down. Okay, so this function is rising first, then there's the apex, and then it's falling again. Okay, so we have quadratic behavior in both directions, and that means the only function that fits well here is f1. So that should be f1. And finally, that must then be f3. And if we look at that to convince ourselves that this is correct, we can again see if we're looking in x1 direction, so walking along these lines here, it's a little harder to plot like that. You can see there's again a parabola, basically. Yeah, and if we're walking in x2 direction along these lines here, those are just falling constantly. So that's just a straight line. So this is exactly the behavior that we would expect from that function f3. Okay, that's how we can recognize the surface plots easily. And now let's look at the level sets as well. So here's one of the level sets. Well, what does this level set correspond to? What happens here is, this is the level corresponding to -5, for example. So each x1, x2 combination along this line here has a function value of -5. Each x1, x2 combination along this line has a value of -3, and so on. Here is -1, 1, 3, 2, 5, and so on. And again, what you can see is the growth is straight in that direction here, and the lines are equally spaced. So the growth is linear. And that means this can only correspond to this level set here. Sorry, this surface plot here. Yeah. So basically, if you're cutting through this surface plot at constant levels of x3, so like taking a cut here, for example, that would mean we get a line like this through that graph. That corresponds to one of these levels. Cutting here at this level, for example, 5, yeah, that means we get a cut like this. And this again corresponds to one of these levels. So you can see those are always straight lines. They are rising. So this is obviously the correct plot for F2. Okay, then what we have here in this level set here, you can clearly see those are parabolas here. So these graphs are parabolas with respect to x1. Here's the x1 axis, so that's parabolas with respect to x1. And that clearly corresponds to this surface plot here. Yeah, again, if you just cut through that graph to get the levels, then what you will see is you get parabolas with respect to x1 here. Okay, so that's precisely what happens for F3. And finally, this here must then be F2. And you can again see the behavior that we just saw with these parabolas, basically. You have these parabolas here with respect to x1, like that. And then you're turning around. And here's also something that looks like parabolas, this time with respect to x2, yeah? Here as well. And here's that point in the middle where things meet, basically. So that's where the one parabola has an apex like that and the other has an apex like that. That's where they meet. So this is what is called a saddle point, where two parabolas coming from two different directions, one opened above, one opened below, those meet here in the saddle point. So you can also see in that surface plot here, this one, somewhere here on that cell, well, you can't see that. That's better. Somewhere here on that saddle point, here, that will be a point where the partial derivatives in x1 and x2 direction are going to be 0. So it's a stationary point with respect to those. So the gradient is going to be 0. But obviously this is not a maximum, not a minimum. So this is how the functions that we discussed in the lectures look like. They have what is called a saddle point. So they're growing in one direction. In this example, they're growing here in that direction and in that direction. And they're falling in another direction like this here. Okay, so that settles 3.6, I hope. I'll copy those graphs here to the notes before I publish them, so you have those as well. So is there any questions about 3.6 before we continue?
No, there was just one question. If you just assigned twice F1 and you scrolled too fast, so I couldn't see.
Sorry, I didn't quite understand that.
So there was one question if F2 is not the linear one, or basically if you assigned F1 twice to the pictures, and I just didn't see because you scrolled too fast at the end. Maybe you can scroll up again.
Okay,
and
did I miswrite something? F1 is this, F2 is this, F3 is this. For 11 sets F2, F3, oh yeah, right, there's an F2. That should be an F1. Yes, thanks a lot. Sorry about that.
yeah,
So that is F1, of course. That's it. Okay, good. So let's go on with 3.7 now. Okay, so in 3.7 we have the set S defined in the following way. We take all points x1, x2 in the plane in R2 with the property x1 plus x2 squared is less or equal to 4. And the basic question is that set open? Is it closed? Is it neither of the two? Is it bounded? Is it compact? Where are the boundary points? Where are the interior points? And so on. And usually if you can, it's probably good to start with a sketch of the set first. So that's part A, draw a sketch of that set to see how that looks like. And often the question of which points are boundary points, which points are interior points, and so on becomes immediate once you have an idea of how that set looks like. So how does that set look like actually? Let's see, we have x1 plus x2 squared is less or equal to 4. Now in this case, this inequality can be easily solved for one of the two variables. In this case, x1 is probably easiest. So let's try to do that. So that's the case if and only if x1 is less or equal to 4 minus x2 squared. Okay, what does that mean? How does that set look like? Well, the first thing that we're going to try is to find the boundary points. In this case, we have less or equal. So that means we can have a look at the equality cases first, and then find out on which side of that boundary of that equality cases the x1 with strictly less than this right-hand side expression actually lie. Okay, so we'll have a look at the boundary case. That is x1 equals 4 minus x2 squared. How does that look like? So what we have here is pretty much a one-dimensional function. The only difference to the ones that you're being used to is, in this case, x2 is the variable. We're usually writing it the other way around. Usually x1 is the variable, and we compute the corresponding x2 value or function value from that. In this case, it's just the other way around. What does that mean graphically? Let's sketch a coordinate system. So what we have is something like this in the setup here. So this is the x1 axis, this is the x2 axis. Now, if x1 equals 4 minus x2 squared, that means we should see something like a parabola. For x2 equals 0, the value of that parabola is exactly at 4. Right? So 1, 2, 3, 4. That's 4 here. So this is the right point for x2 equals 0. Then x1 becomes 4. On the other hand, where do we cross the x2 axis? So where is x1 0? Well, we can reformulate that a little. That is the same as 2 minus x2 times 2 plus x2. So we're crossing the x2 axis exactly at the points plus 2 and minus 2. Okay, so this is here and here. So these are kind of the roots of our turned around parabola. And this is basically all we need to know to get a rough sketch here. So what happens between those points is basically we have a parabola that looks somehow like this. Yeah, it's not very good. Okay, so that's this boundary case here. That is the points where x1 is exactly equal to 4 minus x2 squared. If you don't like that way of thinking, if you rather think of traditional functions, then there's two possibilities. You can either just exchange the rows of x1 and x2, and after that, just rotate the plot by 90 degrees. Or you can, of course, also solve for x2 if you'd rather do that. Let's briefly discuss that. So instead of solving for x1, so the original equation was this here. And again, I'm interested in the coordinate cases, so to speak. So I want the equality case first. Solving this for x2 would mean, well, x2 squared is equal to 4 minus x1. And that means x2 is equal to the square root of 4 minus x1 or minus that square root. Okay, so we get two cases, so to say, plus the square root, minus the square root. And of course, you can also sketch these two graphs independently. That upper part here is the positive square root. That lower part here is minus the square root. That will give you the same result in the end. Okay, so back to the inequality. What we do have actually is x1 is less or equal to 4 minus x2 squared, not equal to. So where are these x1 values that are less or equal to? Well, that means the boundary case here. So this parabola line, this gives us an upper bound for the x1 values. x1 values decrease to the left. So every x1 value below that upper bound is allowed. And that means we can move, for example, from this point here, we can move to the left. From this point here, we can move to the left, and so on. So all these points inside are part of the set. For all the other points to the right here of this parabola, for example, this one here, that's not an allowed point because the x1 value is just too large. Yeah. So this is the set we get. This here is the set S, including the boundary. So is that open, closed, or whatever? That's question B. Is that an open set? Well, if it was an open set, it would only contain, or it would be equal to its interior. So it would contain all of its interior points and just those, no other points. In this case, it's easy to say that this is not true. For example, if you look at this point here, an interior point is characterized by the fact that you can draw a disk around that point, a very small disk possibly, but a disk that is completely contained inside the set, or in general dimensions, a ball rather than a disk. Yeah, this is not the case here. Any disk you draw, like this one here, will always contain points that are outside of the set. So no disk around this point can ever be contained completely in S, no matter how small you make it. For a point like this one here, on the other hand, that would be true, right? I can, for example, I can draw this disk here, that's completely contained in S. Yeah, so this here that is an interior point. This one here is not. It has another property. Every disk you draw around this point contains always points outside of S. That's true. But it also always contains points inside of S. For example, the point itself, the center of the disk. And this is what characterizes a boundary point. Every disk you draw around a boundary point contains both points from inside of the set and from outside of the set. So that works just as you would expect from the sketch, basically, okay? So this line here, this orange parabola line, this is a set of boundary points. No other point has that property, because if we're moving somewhere to this inside of the set, then we can always find a disk, a very small disk possibly, that is completely contained in the set around the point. And if you're moving outside of the set, then we can always find a disk that is completely disjoint from the set. It doesn't contain any points from the set. So no boundary points either. Okay, so this is the boundary. And that means the set S does not just consist of interior points. So S is not open. On the other hand, the boundary of S is completely contained in S. So that means the set is closed. The set is closed if it contains all of its boundary points. Okay, so that means S is closed. And finally, let's have a look at boundedness. That's part C. Is that set bounded? The precise definition of boundedness was there is some disk around the origin that contains that whole set, or some ball in general dimensions around the origin that contains that whole set. So here's the origin. Let's try to draw a ball around that contains the whole set. Well, I'll have to make it at least this large here so that it also includes this point here. Of course, if I do that, I'll end up with a ball that looks somewhat like this. And of course, I mean, I didn't draw that, but of course the set extends beyond that ball here, right, to the left. So obviously, this is not sufficient. And obviously, I can draw that ball as large as I want. It will never be sufficient because, for example, the whole line here, this line here, this one line from the point forward to the left, all of this is contained in the set. So no matter how large I draw this disk, I will never contain all of the set. So that means it's not a bounded set. Oops. Okay, S is not bounded. As it contains, for example, it contains the interval -infinity to 4 included on the x1 axis and 0 on the x2 axis, like this. So all points of the form x1 coordinate between -infinity and 4 and x2 coordinate equal to 0. Let me write this in that form as well. So like this, with x1 in -infinity to 4. Okay, so it cannot be bounded. And finally, compact. Compact means closed and bounded. S is closed, but it's not bounded, so it cannot be compact. It would have to be both closed and bounded. Okay, so it's not bounded, and that also means S is not compact, as it is not bounded. Okay, that's 3.7. What questions do we have about open sets, bounded sets, closed sets?
So yeah, one was just typing, so I have to read that question right now. Yeah, that's actually a good one. So basically, if it is enough in some sense to show openness and closedness in the way you did it right now, or if we ever will use the formal definitions from the lectures again.
Okay, good question. So basically for what we are going to do in this course, it's enough to get an intuitive understanding of what open, closed, boundary point, interior point, and so on means. Yeah, we will usually not use the formal definitions to actually prove that sets are bounded or closed and so on. It's more important that you have an understanding of what that means, how that looks like, that you're able to sketch sets and see which points are interior points, which points are boundary points, and so on, without formally proving that. Okay, so in the form that I just did it, that is sufficient.
Okay, there are still people typing. Okay, one question is, can you explain again the notation in C? Part C.
The notation in C, so I'm guessing it refers to this one here, yeah? Yeah.
Probably, yes.
So yeah, so let me try and explain that. Okay, so this thing here, that is called a Cartesian product or set product. What happens here formally is a thing that I can do with any sets that I want. Let's just take two sets, A and B. To make an easy example, I'll take finite sets in the first step. I'll talk about infinite sets in just a second. So let's take A to be, for example, 1, 2, and 3. And let's take B to be 3 and 5. So those are two finite sets. And I can define this product of the two sets, A times B, that simply consists of tuples. So two coordinates, x1, x2, where the first coordinate is taken from A, the second coordinate is taken from B, and we just form a set of all possible combinations of elements of A and of B. So in this case, for example, x1, that needs to be in A, so that could either be 1 or 2 or 3. x2 needs to be in B, so that could be either 3 or 5. Okay, so the set of all possible combinations, let's just start enumerating them. Start with the first coordinate 1. Then for the second, we could do either 3 or 5. So let's start with 3 and then do 5 next. Like this. So that's all possibilities with 1 as the first coordinate. Then of course, you could also choose 2 as the first coordinate. And again, for the second, we could choose either 3 or 5. So the tuples 2, 3 and 2, 5 are contained in the set. And finally, for the first coordinate, we could also choose 3. So, and again, we have two possibilities for the second. We can choose 3 and 3, or we can choose 3 and 5. Yeah, so that lists all possible combinations of elements from A in the first coordinate and elements from B in the second coordinate. And this is the set product of A and B. Yeah, as you can see, we have these two sets and we get tuples of sets as the result, or a set of tuples rather as a result. And that's just what I did above. So what happens here is basically the same thing. The difference being that this first set here is now infinite. So I cannot just list those tuples anymore. That's why I have to write them in more complicated form. So just write that down again. Again, I'll do an easier example first. for example, consider two intervals, like 1, 2. Here's the first set. And let's say the other one is -1, 1, like this. So that would mean all combinations x1, x2, where x1 is in this interval 1, 2, and x2 is in the interval -1, 1. So if I were to sketch that, let's draw a plane here. Here's x1, here's x2. So x1 varies between 1 and 2. That means here's 1, here's 2. So x1 is somewhere in that interval here. X2 varies between -1 and +1. So here's -1, here's +1. So that's where x2 varies. Okay, and we're doing all tuples where x1 has a coordinate somewhere in this orange area. So I could enclose all of these points here. And x2 has the coordinate somewhere in the green area. So we're interested in all points between those two lines here. And that means the area where both of these meet is this square here. Okay, so this is the set defined as the cross product of these two. First coordinate varies in the first interval, second coordinate varies in the second interval. Just take all possible combinations. So all points with these properties, that's this cross product here. Okay, and to get back to the example that I used above, there we had the product of -infinity to 4, this interval here, with 0. And that simply means the first coordinate varies in that interval here, whereas the second coordinate is always 0. So again, if I draw that, then the second coordinate is always 0. So that means, sorry, that means the x2, x1, the x2 axis will always have a value of 0. Just this one point is allowed. And for the x1 axis, we're moving on this line. 4 is the top value that is allowed, and anything lower than 4 is also allowed. So this here. And we can't move in x2 direction. We're bound to that 0 here. So that means the resulting set will then be just this line here, 4 included. Okay, that's what I meant by this notation here. Again, let me mark that in green here. Okay, final example. You know these already basically. We've often talked about sets such as R2, for example. It's just a convenient abbreviation for R times R, meaning the set of all tuples, x1, x2, where x1 and x2 are both in the same set R. So vectors with two coordinates, both from the reals. Yeah, that's the usual plane. And of course, R3 is just the same, R times R times R, and so on. Okay, I hope that clarifies this. Fabian, any more questions?
Yeah, there was one thing, maybe you could clarify that, because so the question was, the only way to not use the formal definition is drawing or visualizing the graph. And I guess that, I mean, I think we also had some results in the lectures with continuous functions, so maybe you can comment on that, if there are other ways of determining openness or closeness.
Other ways than drawing the graph. Yeah, of course there are.
Or the formal definition, basically.
or the formal definition. What did I do in
Exactly.
the lecture?
No, so what I meant, I think we had the theorem with continuous functions that they map open sets to open sets, but I don't know if you
Yeah, right, we did
mentioned.
that. I
But,
can mention, yeah. So yeah, you're right. We did have a theorem that characterized continuous functions basically through open sets by saying a function is continuous if and only if the pre-image of every open set is again an open set. We will need that at some point later for formal reasons, but I don't really think that clarifies things a lot. So I'd say on the level that we're talking, the easiest way is to somehow visualize the set that we are talking about. And usually it's something that you will be able to sketch or at least visualize it in some other way. And then infer if it's open, closed, or whatever. Or of course we can use the formal definitions. There's examples for that in the lecture. And as you saw there, this quickly becomes complicated. So I would try and avoid that whenever possible. Of course, mathematicians always want to use formal definitions, or at least want to be sure that the formal definitions could be applied. But as I said, for you, it's probably enough to get an intuitive understanding of what these notations mean, what openness means, what closeness means, what boundary point means. We work with these later on, so you need to have an idea of what that is, but you don't need to actually have to work with the formal definitions or beyond that.
okay, I think that's everything for the question 2, or all on the questions for exercise 2.
Okay, so yeah, I hope that was a satisfactory answer. Okay, so let's move on to 3.8 then. So the objective of this 3.8 is basically another example of diagonalization and what you can do with it. So this is pretty similar to what we did with differential equation systems. Let me just give you a very quick introduction to that problem here. You may have heard of the Fibonacci sequence. I think we did that at some point in the lecture as well in the first semester. But just to remind you, the definition is pretty easy. The 0th Fibonacci number is defined as 0. The first is defined as 1. And then you just use a recursive definition. So the k plus first Fibonacci number is simply defined as the sum of the kth and the k minus first. So basically you sum up 2 Fibonacci numbers and get the next one. So for example, if we apply this here, then f2 would be f1 plus f0. So 1 plus 0, that's 1. F3 would then be f2 plus f1. So 1 plus 1, and that's 2. And let's do one more, f4. It's f3 plus f2. So that's 2 plus 1, and that's 3. Okay? And you can see this starts out slowly, but you can imagine the growth will become a lot more rapid once those numbers grow, because we're always adding the last 2 numbers. And as these keep growing, of course, the sum will also grow. Okay, so this is known as the Fibonacci sequence. And the definition is through this recursive formula. So of course, an interesting question is there an explicit formula? And that's the objective of this problem here. So can we compute an explicit formula for some Fn? If I wanted to know the Fibonacci number F100, do I really have to compute all the Fibonacci numbers from 0 to 99 first? Or is there a formula that says, well, take this number to 100 plus this number to 1000 divided by whatever, and there's your Fn. And the idea of this problem here is to show that actually such a formula can be devised. And we use tools from the eigenvector, eigenvalue theory to do that. And those tools are pretty similar to what we did for the differential equation systems. So let's first start with A, with the recursion that we need. First thing that we do is we reformulate the recursion a little. We're extending that to a two-dimensional recursion. Basically, we're starting with a vector of two numbers, f1, g1, instead of just one single Fibonacci number, and we define the starting point as the vector 1, 0. And as you can guess, this g is actually the same thing as g1 is actually the same thing as f0. And that's pretty much the idea here. So we take both an fk and its predecessor of k minus 1 into one vector, so that we have all the values that we need to compute the next Fibonacci number. And we can then formulate this as a matrix recursion. So the definition of Fibonacci numbers then looks like this: fk plus 1. Well, fk plus 1 is fk plus fk minus 1. And we just define gk plus 1 to be equal to fk. Yeah. So this fk and fk minus 1 can also be expressed as gk. Gk plus 1 is fk, so gk is fk minus 1. Like this. And that means we can write this as a matrix vector product. And this matrix vector product has the form 1, 1 for the first row, and 1, 0 for the second row, and then we just multiply with the vector fk gk. Right, so the first row becomes fk plus gk, as we have here, and the second row, this one just becomes fk, like we have here. So this defines a recursion for the vectors. That means we have a sequence, a vector-valued sequence defined through that recursion. And the first coordinate of that sequence is the sequence of Fibonacci numbers. We can now use that to devise an explicit formula. The idea is to come up with a recursion that involves this matrix A and basically reapplies that recursion to get rid of those k's here. Let me just show you what I mean. It's probably much easier. So if we have fn and gn for some arbitrary n, that's the numbers that we want to compute, then you know that this is the same as 1, 1, 1, 0 times fn minus 1, gn minus 1. That's just by definition. Of course, we then can apply this definition once again. So we can say, well, this is the same as this matrix. And then instead of fn minus 1, gn minus 1, we can again write this matrix times fn minus 2. Oops, sorry, gn minus 2. So same thing as 1, 1, 1, 0 squared times fn minus 2, gn minus 2. And if we just apply this again until we get down to f1 and g1, well, how often do we have to do this? So you can see to get down from fn to fn minus 1, we had to apply it once. To fn minus 2, we had to apply it twice, and so on. And basically, we want to get to 1. Well, 1 is the same thing as n minus 1. So we need to apply this thing n minus 1 times. And that's why we have a to the n minus 1 here. Yeah, this matrix here, this is called A. Okay, so this is where that recursion comes from. We now have a recursion for the vectors f and gn. And we can compute f and gn from just the values f1 and g1, which we know, that's 1 and 0, if we are able to compute this a to the n minus 1 for an arbitrary n. Okay, so we can now compute f and gn from just f1 g1. And we know that, that's simply 1, 0. If we are able to compute this matrix A to the n minus 1. And that's the objective of part A here. Okay, let's go on to part B. That's probably the most interesting one. Determine the eigenvectors and eigenvalues of A, and can A be diagonalized? Well, again, this matrix A is 1, 1, 1, 0. So in order to determine the eigenvalues, we will determine the characteristic polynomial PA of lambda. That's the determinant of A minus lambda E2. So we have the determinant of 1 minus lambda, 1, 1, and 0 minus lambda. And that determinant, well, that is simply, let's see, lambda times lambda minus 1, or lambda squared minus lambda minus 1. So we're looking for the roots of this polynomial here. And we can simply compute those using the usual quadratic formula here. So the roots of this are minus minus 1, that's plus 1, plus minus. The square root of 1 squared is 1, plus 4 divided by 2. So what we get is 1 plus minus the square root of 5 over 2. So we have two distinct eigenvalues, both of algebraic multiplicity 1. And that means for each of those, we get an eigenvector. So the geometric multiplicity is also going to be 1. There's no other choice here. So we will have two linearly independent eigenvectors, and that means there is a basis of R2 that consists of eigenvectors of A. So in fact, A can be diagonalized. Let me just quickly note that. Okay, two eigenvalues of algebraic multiplicity 1 each. That means their geometric multiplicity will also be 1. That means we will get two linearly independent eigenvectors. And that means there is a basis of R2 that consists of eigenvectors of A, and therefore A can be transformed. Oops, can be transformed into diagonal form. Okay, so it's possible to do this. We just don't know how because we don't know the eigenvectors yet. And next we are going to compute those. So the next part will be computation of the eigenvectors. Let's start with lambda 1. Lambda 1 is 1 plus square root of 5 over 2. Okay, I'll show this lambda 1. Lambda 2 is basically the same thing. The eigenspace of that is the kernel of A minus lambda 1 E2. So we want the kernel of the matrix 1 minus lambda 1, 1, 1, and minus lambda 1. Okay, what do we do to compute that? We can either just do Gaussian elimination, or just a little more tricky, we could try to eliminate this element here instead of that one. And it would turn out that this is actually a little easier. So what I'm going to do is I'm going to add lambda 1 times the first row to the second. And I'm then getting the kernel of this matrix here. So the first row stays as it is. The second row becomes 1 plus lambda 1 times this expression here, and that's lambda 1 minus lambda 1 squared. And sorry, just move that a little to the right. And the second expression here, this is minus lambda 1 plus lambda 1 times 1. That's going to be 0. Okay, and if you remember the characteristic polynomial, that was, here it is, that was lambda squared minus lambda minus 1. So this here is just minus the characteristic polynomial of lambda 1. And lambda 1 is the root of that polynomial, so that means this expression is minus 0. And that's why things work out nicely. So the first row is 1 minus lambda 1 and 1. The second row is just zeros. Okay, and now we can compute an eigenvector. So span, let's say we can choose either x1 or x2 as free variable. In this case, it's probably nicer to choose x1. So let's say we just set this to 1 arbitrarily. Then we have 1 times 1 minus lambda 1, and the end result needs to be 0. So what is the factor that we need here? Well, obviously we just need the negative of that. So minus 1 minus lambda 1. Okay, or if we want to eliminate that minus sign here, we can also say this is 1 and lambda 1 minus 1. And finally, we do know the values for lambda 1, so we can also substitute those. If you do that, we get 1, and that was lambda 1 minus 1 is then minus 1 plus square root of 5 over 2. Or to make things a little more convenient, the span is the set of all linear combinations of its contents. So in this case, it doesn't matter which scaled version of the vector we use. So for example, we could just multiply this by 2 to get rid of that fraction here. Yeah, so the span doesn't change if we do that. Okay, that's the first eigenspace. And the second eigenspace works in the same way. I'm going to leave that as an example if you want to compute that. The result that you would get here is span minus 2, 1 plus square root of 5. And that means we now have the transformation matrix that we need. We can just use these two eigenvectors here. So by setting S to 2 and minus 1 plus square root of 5 in the first column, and minus 2, 1 plus square root of 5 in the second column, we get s to the minus 1 as equals the diagonal matrix that just consists of those two eigenvalues on the diagonal. Or if you rather write those eigenvalues explicitly, the first one is 1 plus square root of 5 over 2. The second one is 1 minus square root of 5 over 2. And let's call this the diagonal matrix D. Okay, so that's the computation of eigenvalues and eigenvectors. Now before I show you how we can use that to compute a to the n minus 1, let's first see if we have any questions so far. Fabian.
No questions.
No questions. Did I lose you already?
I can't help you with that, sorry.
Okay. So maybe if I did lose you, leave a comment in the chat. So last part. You do remember we wanted to compute a to the n minus 1. And we have computed this transformation to a diagonal matrix so far. So the question is, how can we use that to compute a to the n minus 1? And I'm going to show you the neat little trick now. So a to the n minus 1, we already know there's a transformation. You know that s to the minus 1 as is d. So we can solve that for a. That means a is s d s to the minus 1. We have to multiply with s from the left to get rid of this s to the minus 1, and with s, the inverse of s from the right to get rid of this s here. Yeah, so that's the reformulation solving for a. And then of course we can use this and say, well, that's the same thing as s ds to the minus 1 to the n minus 1. So taking a matrix to the n minus 1 basically means multiplying that matrix by itself n minus 1 times. So we can also write this as s ds to the minus 1 times s ds to the minus 1, and so on. S ds to the minus 1. So this is n minus 1 times. But now this is the same thing as saying, well, s ds to the minus 1, s ds to the minus 1, and so on. Sorry. So what happens here is we can decide which products we want to take first. So we cannot switch the order. It's not commutative, but it is associative. So we can decide to start at the beginning or at the end or somewhere in the middle. And for example, you can also decide to compute this product here first, and then this next one, and so on. And of course, s to the minus 1 times s, that is just E2, the identity matrix. And we can just forget about that one. That doesn't do anything to the product. So what is left is, well, this s on the left, that does not cancel out anywhere. This one here. Then of course all the d's, and there's n to the minus 1 d's. And finally that s to the minus 1 on the right, this one here. That doesn't cancel out as well. So this reduces the whole question to computing d to the n minus 1. But d is a diagonal matrix. You do remember it looks like that. And if you multiply a diagonal matrix with itself, then, well, the diagonal elements hit each other and everything else is hit by zeros. So what you get here is s, then lambda 1 to the n minus 1, 0, 0, lambda 2 to the n minus 1. So this neat trick only works for diagonal matrices, and that is why we can use that here. Okay, so we can now do this computation. Well, we just have to do the multiplication of this resulting matrix here with S and with S to the minus 1. So that's what we have to do to finally be able to compute our end result. So what that means is, what we wanted is A to the n minus 1 times F1 G1. So that basically is the same as S d to the n minus 1 s to the minus 1 times 1, 0. And if you do that computation, I'm going to spare you all the details. What you get in the end is something, well, not quite in the end, but almost in the end, is something that looks like this here. 1 over 4 square root of 5, 1 over 2 n minus 1. And I left one matrix in here, 2 minus 2 minus 1 plus square root of 5, 1 plus square root of 5, and then multiplying this with 1 plus square root of 5 to the n, and 1 minus square root of 5 to the n with that vector here. And basically what we want, if you remember that, is the first coordinate. So we know that fn gn, that was a to the n minus 1, fn g1. So that means we can just use the first row of this expression here to get our formula. And if you do this, the result is 1 over the square root of 5 times 1 plus square root of 5 over 2 to the n minus 1 over the square root of 5, 1 minus square root of 5 over 2 to the n. Okay, so that looks pretty complicated, but it's actually an explicit formula. You just have to substitute in the n, and then you can compute the value of fn. And surprisingly, this actually yields an integer number here. Okay, so you can hopefully see that diagonalization can be a powerful tool. And again, the idea is pretty much the same as with differential equations here. Yeah, we're going to decouple the system by transforming to the diagonal matrix, and then we are able to solve the complicated part. In this case, the power of the matrix. For the differential equations, it was the differential equation itself. We were able to solve that complicated part easily, and that then transforming that back helps us to get the original result. Okay, any more questions, Fabian?
No, not at the moment. There is also no one typing at the moment, so yeah, I don't know. We can wait for a minute, but it doesn't seem so at the moment.
Okay, surprisingly few questions today. So if
okay, now someone is typing, so
good. So we'll wait a minute more to give people a chance to type in their questions. And once more, if your question was not answered today, you're always welcome to attend the tutorials on Thursday. There's actually quite some space available in those tutorials. The links are on the Moodle page, so you're always welcome to join. Just as a reminder, I think next week's Thursday is actually a public holiday. So if you have any questions, you should probably use this Thursday.
Okay, so I don't have a specific question, but much more like a general feedback that the end was a bit fast. So.
Yeah, I'm aware of that. Yes, right. The end was a bit fast. Yes, I didn't do all the computations in detail. Of course, you're welcome to check that, and the solutions that I will publish also contain a few more intermediate steps for those. But you should be able to do those yourselves, hopefully. I just wanted to give you the idea of how this works, how to apply that idea. But you're right, it was probably a bit much for 60 minutes.
And yeah, there's still someone typing, so I guess we can wait for him.
Okay, while we're waiting, maybe a quick announcement as well. I already mentioned that Thursday next week is going to be a public holiday. Usually you would have a lecture on Thursday. So it's probably fair to not prepare too much topics for next week because originally I wouldn't have been able to hold that lecture. So you might have noticed that we got quite a lot of topics this week. Next week will be a lot lighter in exchange for that. I just didn't want to cut back on the examples this week, so that's why it became a little more.
Okay, so no more questions actually.
Okay, good. Then I think we'll close that session. Thanks a lot, Fabian. Thanks a lot for participating and asking questions. I hope I'll see you on Thursday or on next Monday for our next central exercise session. Goodbye.